So the purpose of carbon capture is to remove carbon dioxide from the carbon life cycle. We can do this either at the point of emission, so at flue gas, for example, or we can do it directly from the air. And the reason that everybody's getting so excited about carbon capture is because if we can reduce the concentration of atmospheric CO2, we can reduce the magnitude of the greenhouse effect. As I mentioned, there's a couple of different ways of capturing carbon. Most common is from flue gas, so that's either at the point of combustion or, as David will talk about, at the point of fermentation. So that little picture I've put in there is a whiskey distillery, because something I think a lot of people don't necessarily realise is whiskey distilleries are a fantastic source of CO2 because of the fermentation reaction, but also because of combustion reactions. So typically in flue gas, in something like a CHP, the concentration of CO2 could be as low as 15%, whereas in a fermentation reaction, it could be as high as 95. And so the amount of energy that's needed to capture carbon is partially dependent on the concentration of carbon dioxide in the flue gas itself. There are a number of technologies by which we can capture carbon: absorption, adsorption, membrane, and cryogenic separation. And the energy intensity of carbon capture, as well as being a function of the concentration of CO2 in the flue gas, is also a function of the technology that's used. So there's different technologies for different applications. But energy costs of capturing CO2 from flue gas can be incredibly high. I was recently looking at an energy from waste plant where they thought it would be up to a third of the energy that the energy from waste plant produced would be used to capture the carbon. So very high load is actually sometimes known as a parasitic load. And that is a concern to a lot of companies considering installing carbon capture technology. Where are they going to get that extra energy from? Then we go on to direct air capture. So direct air capture is the same technology suite, but rather than being located at the point of emission at a flue gas or off gas from fermentation, it's directly from atmospheric air. And then finally, we have photosynthesis, which is nature's way of capturing carbon. This has been happening for millions and millions of years. The process of photosynthesis fixes carbon into biomaterials such as trees, grass, and that CO2 is either used as energy for the plant to respire, or it can be fixed in biomatter. So that's the carbon cycle really. Before human activity started to modify it, was that plants would absorb carbon, become carbonous material, which would then potentially go underground and become fossil fuels, or go back into the atmosphere when the tree or the other biomatter decayed. So carbon capture is beginning to get industrial traction. So more and more companies are looking at doing this at scale. The last sort of decade or so has been really dominated by pilot scale projects. The learnings from those have really come to fruition, and we're now seeing all over the world, but particularly in Europe and the UK and the USA, carbon capture projects. So Germany has installed the world's first industrial scale carbon capture and utilization facility at a cement plant. Infinium, based in the UK, who are an energy from waste plant, have just announced investment of £0.8 billion, so huge sums of money into this. A lot of the hydrogen projects that we're looking at, green hydrogen, what makes it green is CO2 is captured at source. So huge industrial traction, which again is where my interest in this comes from. It's a technology that's becoming more and more relevant every day. I want to introduce the concept of biogenic CO2. So not all carbon is alike. Biogenic CO2 is carbon that is derived from plant or animal sources and excludes fossil carbon. So when we talk about carbon capture from green hydrogen, for example, depending on from blue hydrogen is where you generate hydrogen and capture carbon from things like methane. So that's fossil, that's fossil CO2. Whereas carbon dioxide that's generated from fermentation, so for example, in an anaerobic digestion reactor or a whiskey distillery, that's biogenic CO2. And when we talk about the different legislative and regulatory pressures, we'll touch a little bit on why I think this is an important distinction. It's not one that's really been spoken about historically, but it's one that I think is going to come into the forefront over the next decade or so.